Today's lecture will continue a discussion of amines and their various reactions, specifically looking at reductive amination, amine alkylation, and the Hofmann elimination. Before moving into new material, let's review some previous concepts that are going to be very relevant to what we need to talk about today. First, let's look at the mechanism for this reaction. So take a minute, pause the video, and see if you can come up with the mechanism. Note that you have a bromine that is disappearing as well as an acetyl group that is leaving. Okay, let's see how you did. The first step, the most likely thing to happen first, would be the hydroxide removing the hydrogen from the beta position. So this is the bromine leaving group. The carbon underneath it is the alpha carbon. The carbon adjacent to it is the beta carbon. Hydroxide pulls that hydrogen off and we form a double bond. This pi bond right here is conjugated with the rest of this bicyclic ring system. This carbon is sp2 hybridized, sp2 hybridized, sp2, sp2, so it's most likely that that's where you're going to form the pi bond. Plus, you saw the product. The acetyl group right here, if I draw it out in all of its chemical glory, the hydroxide is going to hydrolyze that. This is an ester, and so this is just a base catalyzed saponification of an ester. Hydroxide attacks the carbonyl group, the oxide ion drops its electrons back down again and pushes off our organic compound. This part that we don't care as much about goes on to become acetic acid, which immediately gets deprotonated, probably on the way out the door, to put the hydrogen on the phenol portion of the ring system right here. The purpose of looking at this particular reaction was actually to focus on the phase transfer catalyst. So here's a quaternary ammonium compound, a quaternary ammonium hydroxide. And the hydroxide would be in this solvent. S stands for solvent, so it's in the aqueous solvent. The organic solvent would be THF, and this phase transfer catalyst would cart the hydroxide back and forth between the water and the organic compound. So the purpose of this question showing up as a review in this chapter is to remind you of some basic chemistry that we saw in previous chapters, but also to look specifically at the role of phase transfer catalysts. Here is another review quiz. This is a catalytic hydrogenation reaction, and you need to figure out what the products are going to look like, what the product is going to look like. Okay. Catalytic hydrogenation typically hydrogenates alkenes, so that one you should have seen as being hydrogenated. And then it will hydrogenate a carbonyl group that is part of an aldehyde or a ketone, but not a carboxylic acid or an ester. So neither of these two carbonyl groups, these pi bonds, would be left alone during catalytic hydrogenation. It's this pi bond right here between a carbon and a nitrogen that was the point of this question. And this is an imine, and imines will undergo catalytic hydrogenation just like ketones and aldehydes to produce just a regular amine bond right there. This is not necessarily a review, more of a preview of a type of reaction we're going to look at in today's lecture. Third review quiz. Pause the video for a minute and see if you can come up with the product of this reaction. Give up. This one was hard. The product for this one right here is an imine. So this is a ketone. The ketone reacts with ammonia to form an imine. We're going to review the mechanism for imine formation today. We saw this a few chapters ago, but it's been a while. There are several other ketone-looking things going on inside of the compound. They're carbonyls. This carbonyl is a cross between an amide and a thioester. This one is a thioester. But more importantly, they're part of an aromatic ring system. So everything inside of the ring system would be sp2 hybridized. There is a lone pair donated by the sulfur, a lone pair donated by the nitrogen, and this pi bond right here giving it 6 pi electrons, so this is fully aromatic. And if you try to plug a nitrogen into that carbonyl group or that carbonyl group, your intermediate would lose aromaticity. So it's much more likely for the nitrogen to plug into that carbonyl group, and the rest of these carbonyl groups are essentially spectators. Okay, the topics that we're going to look at today, first is reductive amination, and we're going to do that through imines and enamines. Part of the review quiz was to review the formation of imines and enamines. So here's a slide from a previous chapter, reaction of primary amines with carbonyl groups. So here's a primary amine under acidic conditions, and these need to be either mildly acidic or mildly basic, and either one would work. The first thing would happen under acidic conditions is the preprotonation of the carbonyl oxygen, then the attack by a nucleophile, then the deprotonation of your nucleophile. And these 3 steps, preprotonation, nucleophilic attack, deprotonation of the nucleophile, were 3 steps that we saw over and over and over again in previous chapters. This right here is called a carbanolamine. This is the tetrahedral intermediate, and then we're going to go through those same 3 steps again. Preprotonation of the carbonyl oxygen, or what used to be a carbonyl, an internal nucleophilic attack, and then a deprotonation of the internal nucleophile. And this is the imine, which is a carbon-nitrogen double bond. And again, this is a reaction that we looked at before, and this is what we expect with primary amines, or as we saw in the review quiz, ammonia reacting with a carbonyl group. So if we don't have a primary amine, but rather have a secondary amine, then instead of forming imines, we end up making enamines. Going back to the previous mechanism, notice that the 3rd step, so 1, 2, and in this 3rd step right here, we had to deprotonate the nitrogen nucleophile. A secondary amine has that proton to pull off, so we can go through that step to the carbanolamine, but then after the internal nucleophilic attack, a secondary amine would not have this hydrogen right here. That's why primary amines and ammonia will make imines, but secondary amines have to do something else. So here's the mechanism for a secondary amine. This is done under basic conditions. You can do either acid or base, it doesn't matter. The nucleophilic nitrogen attacks the carbonyl group, and then we deprotonate the nucleophilic nitrogen. We preprotonate the oxide ion right here, and this acidic nitrogen came from deprotonating the nitrogen nucleophile in the previous step, and we get to this same carbanolamine right here. So same thing that we saw for both the primary amines and now secondary amines. The problem is when this internal nucleophilic attack occurs right here, now there isn't another hydrogen to pull off that nitrogen. So instead, we pull a hydrogen off of the position away from the carbon. So 2 positions away from this nitrogen, you pull one of the hydrogens off. 2 positions away from the nitrogen on this side, that's a phenyl group and it doesn't have a hydrogen. So this is where the hydrogen is going to be pulled off, and we end up with an alkene attached to an amine. That's where the term enamine comes from. And so the purpose of these 2 mechanisms was to review the formation of imines and enamines that we saw in a previous chapter. So why do these show up again? And the answer is, well, we're going to do something with imines and enamines that ultimately ends up producing just regular amines. So here's an example. This compound right here, this is a ketone, and there's some other stuff going on, but it's the ketone that we're interested in. We're going to react this with ammonia, and the ammonia will react with the ketone to form an imine, but we're going to simultaneously catalytically hydrogenate this thing. And so instead of producing an imine, it skips all the way. We're doing this all in one reaction container. We form the imine, which would involve a carbon-nitrogen double bond right here, but catalytic hydrogenation will hydrogenate that imine as it's formed, and we end up going from imines directly to amines, skipping through an actual step where we have to isolate the imine and then run the catalytic hydrogenation. You just do this all at once. Here's another example of this, only this time I have a secondary amine. The secondary amine is going to react with an aldehyde, and we're going to end up catalytically hydrogenating that at the same time that the reaction is occurring. And that will end up producing an amine. So regardless of whether we go through the imine or the enamine intermediate, catalytic hydrogenation will take it all the way through to the amine. Here is so this was reported in the literature, and they used acetic acid. So the reaction that I showed you before for the formation of enamines was under basic conditions. The authors of this paper did it under acidic conditions. Under acidic conditions, we pre-protonate the carbonyl oxygen. Then there's a nucleophilic attack by the nitrogen and a deprotonation of the nitrogen nucleophile. That gets us to our carbanolamine intermediate. So then we do a second round of protonation of that same carbonyl oxygen, an internal nucleophilic attack to bump off water as a leaving group. And we get to this point right here, and instead of forming the enamine, the hydrogenation occurs directly at this point. And since if we did want to form an enamine, then the conjugate base of acetic acid, the acetate, would end up pulling this hydrogen off of the alpha position. And so we would use our acid, and then we regenerate the acid, and we use the acid, and if we were just making an enamine, we would regenerate that acid. So it wouldn't be a reagent, it would be a catalyst instead. And the authors said it was a reagent, and I'll take them at their word, which means that the catalytic hydrogenation occurs on the iminium ion. I think that's what you call that. But this nitrogen-carbon double bond with a positive charge, and the hydrogenation occurs right there. So again, the point of both of these is that we can take ketones and aldehydes and turn them into imines and enamines, and then if we couple that simultaneous with catalytic hydrogenation, you go right through all the way to the amine. Sometimes, though, in that catalytic hydrogenation, you want to be specific about what you're hydrogenating. So consider this example right here. Here is an amine, and I'm going to react it with, this is a alpha keto acid, but here's my ketone right here. The nitrogen will react with this carbonyl group to form an imine. This is a primary amine, so it will react with my ketone to form an imine. You can kind of see what that product looks like, only we don't have a double bond here. And that's because there is an alternate reducing reagent called sodium cyanoborohydride. It's this compound right here. The sodium is a spectator ion, so it's really the cyanoborohydride that does the reduction. The mechanism for that we're not going to look at, but the rationale for it is important, because if you try to run this same reaction under conditions of catalytic hydrogenation, in addition to hydrogenating the imine bond, you would also hydrogenate the alkene. And this was the compound that we looked at the hydrogenation of during the review quiz. So why wouldn't catalytic hydrogenation work for this reaction? Because catalytic hydrogenation is not specific. It would hydrogenate the imine and the alkene. Cyanoborohydride is specific. It specifically reduces the imine. So that's about it for reductive amination. We looked at how we can make imines, and then we can make enamines, and we can reduce either of them with catalytic hydrogenation or cyanoborohydride if we need to be specific about what it is that we're actually reducing. The next two topics for today are amine alkylation and Hofmann elimination, and these two kind of go together. I'm going to attack them both at the same time, but in order. So first, let's look at amine alkylation. This is usually not a very productive reaction. So here we have a diamine, and the authors in this particular research paper reacted it with 5 equivalents of deuterated methyl iodide. And what you'll notice is that these nitrogens right here picked up 5 total methyl groups, deuterated methyl groups. And that's kind of hard to stop. Once the amine alkylation process gets started, you really continue to go until the nitrogens have reacted with as many alkyl groups as they possibly can. Mechanistically, if we think about what's going on here, the nitrogen is attacking the methyl group, bouncing off the iodide, and then the authors simultaneously added in lithium hydroxide. The hydroxide deprotonates that nitrogen, and now the nitrogen is reloaded and ready to undergo another round of alkylation. So this nitrogen right here, with its lone pair, can now react with a second equivalent of the deuterated methyl iodide. And that process continues until the nitrogens eventually stop. And every time they undergo this reaction, they actually get slightly better at it in many cases because the alkyl group is electron donating. And we looked at this before as the whole reason for the Gabriel synthesis. The Gabriel synthesis avoids the tendency of amines to alkylate as many times as possible. In this case, the one nitrogen up on top in this particular diagram alkylated 3 times, and the nitrogen on the bottom alkylated only twice. So why did it stop at 5 alkylations? Why didn't the bottom nitrogen also alkylate 3 times? Well, that's what the data suggested, but it's probably also because once you get a positive charge on this nitrogen, then that starts to present a problem. This nitrogen has a hard time attacking electrophiles because the positive charge is kind of pushing them away. So it stopped at this point. Notice too that the authors only added in 4 equivalents of lithium hydroxide, and I thought that was interesting. Normally you don't ration out your hydroxides carefully, you just throw a bunch in there. But that's why they published this. They knew what they were doing. They got the lithium hydroxide with 4 equivalents, and that's because each hydroxide had to take off one of these hydrogens. So once you take off the 4th hydrogen, there's no more hydrogens to remove, and therefore no more hydroxide that is needed. And this is just the solvent right here. So the reason that you do amine alkylation is generally to set up for a Hofmann elimination. So the two go together. If you want to put an alkyl group on a nitrogen, usually you use the Gabriel synthesis so that you can carefully control how many alkyl groups you add to your nitrogen. And you control it so that it's just one, and then you're done. With alkylation, it tends to add multiple alkyl groups, which is difficult to predict and hard to control and leads to low yield. So why would you ever want to alkylate? Well, this has to do with the Hofmann elimination. And the Hofmann elimination is more of a generic term than the way that I'm going to use it today. Often it refers to the formation of the less stable alkene. So here are 3 different reactions. All of these are E2 elimination reactions. The first 2 are ones that hopefully you're familiar with, or when I talk about them, hopefully you kind of remember what's going on here. An alkyl halide in the presence of an alkoxide base will typically undergo E2 elimination. This methoxide would end up pulling the hydrogens either from this carbon or this carbon right here. If the methoxide pulled the hydrogens from this carbon, then we would end up with this as our product. We would also end up with this cis alkene as our product, but we expect that to be a minor product because it's thermodynamically unfavored. If instead the methoxide comes over and pulls the hydrogens off of this position, we would make 1-butene, and that's a minor product. And Zaitsev is typically the one that we mention when deciding which carbon to remove hydrogens from. Zaitsev's rule tells you that you pull the hydrogens from the carbon with the fewest number of hydrogens. And there's plenty of exceptions to Zaitsev's rule. This is not an exception to Zaitsev's rule. We would expect Zaitsev's rule to tell us that this would be the major product. One of the ways that you can produce an exception to Zaitsev's rule is by using a sterically hindered base. And while Zaitsev would tell you to pull the hydrogens off of this position, this base is so large and bulky that it has a hard time accessing this position, and instead kind of hangs out on the outer fringes and pulls off these hydrogens that are easier to get to. When I taught this earlier, I called this an anti-Zaitsev elimination, simply because it fit nicely when we talked about Markovnikov and anti-Markovnikov addition reactions. But the more common way of talking about this is to call this a Hofmann elimination. And the Hofmann elimination is best characterized by eliminating a large, bulky leaving group. This is a case where the leaving group isn't bulky, it's the base that is bulky. And that produces this anti-Zaitsev or Hofmann elimination product. What we're going to look at today are large, bulky leaving groups and how they have a tendency to produce a Hofmann elimination product, or a product where the alkene is less substituted than other alkenes that you could potentially form by eliminating that same leaving group. Notice that this bulky leaving group is a quaternary ammonium hydroxide. And that is an ionic compound that you can synthesize, and then you just heat it up, and that activates the hydroxide as a base, and the base pulls off one of these two hydrogens right here. Because the major product shows one butene, then we should know that the base is pulling off the hydrogens out here from the outer edge. Here's another example of this and how you would couple the amine alkylation that we looked at previously, now with the concept of Hofmann elimination. So here is primary amine. We're going to react it with an excess, that means a lot of, methyl iodide in the presence of hydroxide. And just like the mechanism we looked at before with the deuterated methyl iodide, this regular methyl iodide will get attacked multiple times by the nitrogen. The hydroxide will keep pulling off hydrogens until eventually the nitrogen is fully loaded with methyl groups, and now we have a quaternary ammonium iodide salt. That quaternary ammonium iodide is changed out for a quaternary ammonium hydroxide by using silver oxide in an alcohol water solvent. Silver will form a precipitant when you mix it with any of the halide ions that we typically use, chloride, bromide, iodide, and that formation of a silver iodide or silver chloride or silver bromide precipitant will drive the equilibrium. And essentially this is an ion exchange reaction, not really an organic reaction. It's just this oxide pulls one of the hydrogens off of the water, forms hydroxide. The hydroxide replaces the iodide in an ion pairing, and the iodide complexes with the silver and falls out of solution and drives the equilibrium forward. So there's no real mechanism here. It's just you need to understand the chemistry, that we can show the mechanism for the amine alkylation, and then we have an ion exchange reaction, and this sets up the Hofmann elimination. Once you form this salt right here, when you heat it up, the hydroxide will end up bouncing this quaternary ammonium nitrogen off of the compound via E2 elimination. I'll look at the mechanism in just a second, but let's first focus on what the products look like. This large, bulky leaving group has a tendency to produce the anti-Zaitsev or Hofmann elimination product. This is the carbon that is attached to my leaving group, therefore this is my alpha carbon. The beta carbons are here, here, and here. These two beta carbons are equivalent, and this beta carbon over here is the one that is kind of easier to get to, the less substituted beta carbon. And for these quaternary ammonium compounds, this carbon is the one that loses its hydrogen. So when the hydroxide pulls the hydrogen off there and we form that alkene, this represents my major product. It is less likely for the hydroxide to pull the hydrogen from one of these two beta positions, and this is unique. This isn't what we saw with alkyl halides. We would have expected this to be the major product if instead of this as a leaving group, we just had a bromine on there. So now we need to understand why. Why is it that the Hofmann elimination product ends up selecting for the less substituted pi bond? Well, first let's consider the mechanism. And so here I have two different routes to produce the product. So I'm taking the same compound right here, and when I heat it up, that hydroxide, which previously was just kind of a comfortable ion balancing out the charge, now is angered, becomes an active base, and is going to pull off one of the hydrogens from a beta position. Now here's my leaving group. This is the alpha carbon. There's a beta carbon, beta carbon, beta carbon. I'm going to focus on these two beta hydrogens because they are representative of the different types of beta hydrogens that exist. In the blue pathway right here, this is what Zaitsev would have told us to predict. The hydroxide will pull the hydrogen from the carbon that has the fewest number of hydrogens and produce a tri-substituted alkene, which is thermodynamically more stable. The Hofmann elimination product pulls the hydrogen from the carbon that has more hydrogens, produces a di-substituted alkene, which is thermodynamically less favorable. When you have these nitrogen leaving group compounds, then this is the major product that we expect. The reason why the Hofmann elimination produces the less stable alkene has to do with the steric consequences of a large leaving group. I'm going to cover up the image down here on bottom just that you look at the thing that I want you to look at. So consider this example, a fairly simple example. This is a butane, and on the 2 position of the butane I have a leaving group. The leaving group happens to be this very large nitrogen group right here. And the hydroxide is complex with this. We heat this up and that activates the hydroxide as a base. This is my alpha carbon, and therefore I have a beta carbon here and a beta carbon here. In order to understand what's going on, I need to focus on the Newman projection that leads to the formation of my product. So let's think about how I would get the cis-2-butene out of this. In order to form a double bond between carbon 2 and carbon 3, this is carbon 2 and this is carbon 3, I need to pull the hydrogen off of carbon 3 right here. I'm going to go ahead and redraw this compound as a Newman projection, where my eyeball is over here and I'm looking down the barrel of the C2-C3 bond. So this carbon right here is the carbon that's in front. That represents carbon number 2. And the big circle is the carbon in back, and that's carbon number 3. Coming off the carbon in the back, this carbon number 3 is just a methyl group and 2 hydrogens. Off the carbon in the back is a methyl group and 2 hydrogens. The carbon in front has a methyl group, the nitrogen ion, and another hydrogen. The carbon in front has a methyl group, the nitrogen ion, and another hydrogen. In order for elimination to occur, the leaving group must be anti to the hydrogen that's being pulled off. So this is the leaving group on the front carbon, and the hydrogen in the back carbon that's anti to it is the one that's going to be removed. When that hydrogen gets pulled off and the leaving group leaves, then this compound flattens out. With this hydrogen gone and that nitrogen gone, then these 2 methyl groups actually pinch closer together as the thing flattens out. Those 2 hydrogens pinch closer together, and that's how spatially you go from this Newman projection right here to the Z2-butene. Notice how the methyl groups are on the same side, the methyl groups are on the same side. Okay, now let's look at what would happen to make the other 2 compounds. So if you're going to make let's go back to this trans-2-butene right here. In order to make the trans-2-butene, I would still pull the same hydrogen off that I pulled off in order to make the cis-2-butene. So the trans-2-butene would involve pulling a hydrogen off of C3 and having your leaving group pop off of C2. So my Newman projection needs to be looking at C2 in front and C3 in back. Okay. Here's C2, and there's C3 in back. And notice the difference between forming the trans product and forming the cis product is that I just had to rotate the back carbon. So here's the Newman projection to get the cis-2-butene, and here's the Newman projection to get the trans-2-butene. If we look what's going on here, this large bulky group has one unfavorable gauche interaction right here with a methyl group. On the gauche on the other side is a hydrogen. Going back up to the cis-2-butene, that large bulky group has a gauche interaction here that's unfavorable, and this methyl group here also has a gauche interaction that's unfavorable. So while we typically like to explain that the trans is formed more likely than the cis because the trans is less sterically hindered, you can also see that in the moment that you're trying to make your trans double bond, there's actually less gauche interaction than when you're trying to make the cis double bond, which has 2 different gauche interactions. So gauche here and gauche here, whereas the trans only just has the one gauche right there. So from kind of an intermediate perspective, it makes more sense that we would make E2-butene. So even though I said both of these 2-butenes are minor products, this is kind of your minor product, and this is your minor major product. All right, enough of the minor products. Let's focus now on the major product. In order to end up with 1-butene, that means that I needed to pull the hydrogen off of carbon number 1. Just to kind of maintain some consistency and perspective, my Newman projection is going to still look at carbon number 2 in the front, but now it's looking at carbon number 1 in the back. Carbon number 2, if I'm looking at it this direction, has the nitrogen ion, the ethyl group, and a hydrogen. Here's carbon number 2 with the nitrogen ion, the ethyl group, and the hydrogen. The carbon in the back, this methyl group right here, has 3 hydrogens, hydrogen, hydrogen, hydrogen. Notice that in this particular orientation, I can line up my hydrogen anti to my leaving group, and I don't have the same gauche problems. So I'm not restricting the molecule to adopt unfavorable gauche interactions by pulling the hydrogen off of this position. And this is how we use Newman projections to explain why a sterically bulky leaving group tends to favor elimination so that it produces the less substituted alkene. That's because in the Newman projection right here, we can line that hydrogen up exactly where it needs to be, and we don't have the same number of unfavorable gauche interactions. Let's look at this in another example, and so now it's your turn. So what you should do is, I've shown you here the major Hoffman product. We formed the less substituted alkene. So when the elimination occurred, we ended up pulling a hydrogen off of this carbon to form the alkene right here, and not the hydrogen off of this carbon to form the alkene right here. So what you need to do is pause the video and draw the Newman projection that would lead to this product, and compare it to the Newman projection that would have put the double bond right here. So go ahead and try that. Well, let's see how you did. Here are the 2 Newman projections. In forming the major product, the one that's shown, I am going to put this carbon right here in the front of my Newman projection. So this is carbon number 2, and this carbon right here is carbon number 1. So carbon number 2 is in front of the Newman projection right here. Carbon number 1 is in the back. Carbon number 1 is the easy one. It's got 3 hydrogens coming off of it. So my back carbon right here has 3 hydrogens. The front carbon has a methyl group. This is an isopropyl group in the large nitrogen ion compound, or portion of the molecule. And so here's the methyl group, here's the isopropyl group, and here's the large nitrogen. And no matter how I rotate this, I don't have any problematic gauche interactions when I try to put the hydrogen that needs to be plucked off anti relative to the nitrogen leaving group. So this explains why this is the major product. Now let's try a Newman projection where I would have produced the minor product. And the minor product would be pulling the hydrogen off of this carbon, that's carbon number 3, and having the leaving group pop off carbon number 2 and forming a double bond right there. So this Newman projection over here puts carbon number 2 in the front and carbon number 3 in the back. Carbon number 3 has a methyl group, and a hydrogen. Off the back carbon I have a methyl group, and a hydrogen. The carbon in the front has 2 methyl groups and the large nitrogen ion. 2 methyl groups and the large nitrogen ion. In order to line up the hydrogen off the back carbon so that it's anti-relative to the nitrogen leaving group, notice I have gauche interactions essentially everywhere possible. And so in order to avoid this type of steric strain, this compound would rotate so the methyl group is anti, the hydrogen would more likely be found here, and that would reduce the probability of the elimination ever occurring because this hydrogen is simply unlikely to be anti to my leaving group. This is the rationale for the Hofmann elimination.